one application of integrations is finding the area of regions between curves, okay? And we'll sort of look at two broad situations. The first one is where the area bounded by the curves could be described by functions of x, okay? And what do we mean by that? Well, take a look at the plot on the left-hand side here. If we want to find the area of the region bounded by these two curves, okay, notice that the curves pass the vertical line rule, okay? The curves pass the vertical line rule. And what does that mean? That means they're functions of x, okay? And so that's what we mean by region bounded by functions of x. The curves that bound that region could be described as functions of x. So the top part is f of x, the bottom part is g of x. On the left-hand side, we have a point of intersection. They intersect at A. Okay, sometimes we have to find out where they intersect if that's what the question asks us. And on the right, we just stop at B. We just call it quits there. Okay, and so this region, its area, is given by this integral right there. Okay, and here notice that f is greater than g. Okay, it's all right for the functions to be negative, but f is greater than g everywhere. That part's important. But even if say over here g of x is negative in this portion, well, for a net area that's going to give you a negative net area. That's all right. You'll have a positive number minus a negative number, which is just adding these then two areas. And so it does work out for situations where the functions are negative, but f of x should be greater than g of x. Well, what if we run into a situation where you fail the vertical line rule? Take a look at that. Here we're failing the vertical line rule, okay? But we pass the horizontal line rule. We do pass the horizontal line rule. And so rather than these curves being functions of x, which you can't, right? It fails the vertical line rule, but they are functions of y. So here x is the output and y is the input, and that does work. You do have functions of y that output x, okay? And if you want the area of a region that we see on the right-hand side there that's described by a region bounded by functions of y, then again, assuming fy is greater than gy, which here that means fy is more to the right than gy, because x increases as you move to the right. So with fy greater than gy, you have this integral here, okay? And again, this works for functions in which x is negative. So over here, that's negative, but you do need to make sure that fy stays greater than gy on that interval. And likewise, you might have a situation where you're integrating a region from a point of intersection, which you might have to solve for. So like C over here up to D. And so here we'll have our integral from C to D to get the area of the region bounded by those curves described by functions of y. Okay, so let's take a look at some concrete examples. Here we want to find the area of the region R in the first quadrant bounded by the curves y equals x to the 2/3 and y equals x minus 4. So your first instinct is that, well, these are given by functions of x, right? So y is the output and x is the input. But if you plot it out and you take a look, this part here that says first quadrant constrains us, okay? Because it's not the area of the region bounded by the two curves y and y equals x to the 2/3 and y equals x minus 4, but also it must be on the first quadrant. And so what we effectively have, if we do that, is that for our bottom function, g of y, we'll have a piecewise function, okay? On the left-hand side here, over here, g of y is just 0, so you just integrate with that being the upper function and the bottom function being g of y equals 0. And then as you move past 4, you have your g of y being this x minus 4 and your f of y being x to the 2/3. And so this is a piecewise function for a bottom function. Okay, and we had to do that again. Why? So we could stay in the first quadrant. The bottom function drops below the first quadrant if we keep going to the left of 4. And so we could break up this region into two different regions. One here in green, where the top function is x to the 2/3. And I didn't write it here, but you'll have a minus 0 for the bottom function. And the right-hand side in orange there is from 4 to 8. And you have y is equal to x minus 4. You carry out the integral, you get the final answer. But get this, okay? These functions are functions of x, right? They do pass the vertical line rule. But they also pass the horizontal line rule. And now, if we don't want to break up our integration into two different integrations, to break it up in a piecewise fashion, what we could have done is just recognize that, they pass the horizontal line rule, and that this integration can be carried out from y equals 0 to y equals 4, okay? So we could have carried out that integration from y equals 0 to y equals 4. And now what is the rightmost function? The rightmost function is the one in pink here, the magenta. Yeah, or if you solve for it, you'll get x is equal to y plus 4. And if you solve for x over here in terms of y, you get x is equal to y 3/2, okay? And so these are functions of y as well as functions of x, okay? Now let's look at it. Let's focus now on the functions of y view. This is the rightmost function. This is the leftmost function. So the x is equal to y plus 4 is greater than x is equal to y to the 3/2 on the interval 0 to 4. That interval is for y. And so you get this integral. Now, if you take a look at the right-hand side here, okay, this graph, be very careful because look at that. That's not the x-axis, okay? That's the y-axis. And over here is the x-axis. So I flipped around the x and y axes so you could see what's sort of going on. I mean, when we look at it from this perspective, integrating over y, it's intuitive now. Taking a look at that integral, sometimes if you're looking at it from left to right, it's kind of confusing, but we're kind of used to looking at things vertically. Well, you see that if you flip around the x and y, they do pass the vertical line test. And so, indeed, these are functions of y. And you do see that the top function is y plus 4, and the bottom function is y to the 3/2. Okay, now we had to solve for x in terms of y if we're going to integrate with respect to y. So that's super crucial. Okay, and all we have to do now, we just have one good old-fashioned integral. We take it out from 0 to 4. We carry out the integration. We get the same exact answer that we got before. And there goes another application of knowing how to integrate.